This is Unit 2, Topic 1, Basic Concepts of Probability. In statistics, probability is not really a topic that we emphasize. We do use a lot of probabilities within statistics, but we don't spend a lot of time making calculations like you would typically think of if you did probability in a math class. However, we do need to gain an understanding of probabilities enough that when we are encountering them, that we're able to understand what they mean. This unit is pretty different from the first unit, which I think for the most part is a good thing. While there is a lot of things in Unit 1 that you're probably already familiar with, it definitely has a lot of aspects to it where it could be one or the other depending on your explanation. And that is reality, but I find that students don't usually favor those types of material. So our unit here has two separate sections to it. The first four topics are the probability sections. So we're going to find traditional probabilities again just enough so that we understand them very well when we're exposed to them. Then we kind of take a turn into more of what we would like to accomplish in statistics, which is using these probabilities to answer questions. So it's going to be about less of the calculations of the probability and more about the technology that we use, which will calculate most of our probabilities for us. So this first topic begins with a few definitions. The first is the word probability. We're going to define that as the likelihood of an event happening. So we're going to look at a lot of different probabilities throughout this unit, and we'll get pretty comfortable with them is the goal. Next, we have an event. That is a collection of results or outcomes for a procedure. So the definition I don't really think is an enhancer of this word. An event can be anything from flipping a coin to the weather that can occur in a day to the outcomes that you can get on your statistics exam. So an event is all of the possible outcomes put together. And then lastly, sample space is when you actually define each of those individual units. So an event and sample space are pretty similar, and they are, but an event is usually a description of the event to happen, and the sample space is describing in detail each of those outcomes for that event. So before we actually get into a few examples, there are a few properties of probability. These are pretty important. This section is going to be pretty rule oriented, which we'll feel we will be for the rest of the course, but this is where we start getting a little bit technical. So first is notation. Notation can be pretty annoying, but it's also really important in statistics because notation is one of the major ways that you will communicate. So P of A is the probability that event A will happen. So A could be the probability that it will rain tomorrow. It could be the probability that you pass your statistics test. The second, a probability is a number between 0 and 1 inclusive, meaning that 0 and 1 are included. A lot of you guys are going to want to use percentages, and that's totally fine. I definitely, in my head at the very least, will convert every single probability to a percentage. But when a question asks you for a probability, it's always the decimal value. So this is something that there are some cases where you can get in trouble if you don't write your probability as a decimal. But for the most part, percentages are a lot more reasonable and people are able to understand them more easily. The probability of an impossible event is 0. So 0 and 1 inclusive means that 0 and 1 are included. 0 is always going to be an impossible event. And the probability of an event certain to occur is 1. So technically, the probability that tomorrow will happen is not necessarily 1, but it's probably 0.99999 for a very long time. The way that we're going to be constructing our probabilities is P of A is equal to the number of ways event A can occur divided by the number of outcomes for the procedure. So this is basically your traditional part over whole. If that's how you looked at fractions, it's going to be almost the same exact thing here. An event is considered unusual if its probability is less than 0.05. And we will find that this should bear some similarities to our range rule of thumb, as well as that linked up with the empirical rule from Unit 1. Finally, we will be rounding all probabilities to 4 decimal places. I will specify this as much as possible. If you round to 3, it's not the end of the world, but rounding anything less than 3 is pretty severe, because if you did convert to a percentage, then you would be getting close to being off by a whole percent. So I'm always going to be rounding our decimal places to our probabilities to 4 decimal places, and I would like you to as well. So everybody is familiar with probabilities. They're encountered on a regular basis, but I find that it's not always common that people interpret probabilities correctly. So an example I'm going to say of this is that I play World of Warcraft, and there was a guy in general chat just complaining and complaining because he kept on doing this quest that had a 60% success chance, and he kept on failing it over and over again. And so somebody in the chat actually jumped on this first, but the person in the chat was just like, hey, 60% means, that 6 out of 10 times you're going to get it. So if you failed it 3 times in a row, that's not really that crazy. So if he failed it 100 times in a row, then I would say the 60% is a lie. But with probabilities, it's over time that we'll find that those probabilities will come to life. So if you flip a coin, the probability of getting a tails is 1/2, 0.5. So in those blanks, I would like you to convert 0.5 to a fraction, which I've already given away, as well as to a percentage, and that will be displayed on the bottom of the slide. What this means, though, is that getting tails at 50% means that if you flip the coin over and over and over again, that 50% of the time you'll get tails after a very long period. If you flipped a coin 10 times, you will not always get 5 heads and 5 tails. So I find that people will always understand this and can kind of feel this idea at, flipping a coin level. But it applies exactly the same thing when it's things like weather or other types of places that you'll see probabilities. So what we will do later on is we'll practice this in just a little bit, and we'll get a chance to see how these probabilities end up working. So there's our percentage and fraction for our decimal. So to interpret a probability, you may decide that a fraction is actually a better way to think about it. And usually people don't think that fractions are favorable in any way, but I actually think that it makes a lot more sense than the actual percentage does in some cases. So a 0.5 probability means that there will be a result of tails 50% of the time after a large number of flips, or you could also look at this. So 50 is 1/2. 0.5 is 1/2. So every 1 out of 2 flips in general will result in tails, again, after that large number of flips. So the next activity is part of your learning quiz for this week. So if you do this along with the slide, definitely make sure you keep these results because they will be part of the assignment identically as they are here. So you can use this random.org/coins, or you can actually flip a real coin. It's completely up to you. But what we're going to do is we're going to do 10 trials of flipping a coin 10 times. We're going to examine how, for each individual trial of 10, what those percentages of tails end up being. And then we're going to pool everything all together and see how that ends up being over time. So this is pretty similar to what you will have on your learning quiz for the week, except for it's not as color-coded. But we're going to have, again, 10 times. We're going to have 10 sets of 10 flips, and we're going to fill in this table here. I would probably just do the lab activity right along with this, 2 birds with 1 stone. So what I'm going to do is I'm going to move this over and go to random.org/coins. And so again, you can flip a regular coin. There's no advantage or disadvantage. If you want to, you can flip 10 coins at once. It's a pretty convenient advantage of using something on the computer. And so this is called a simulation. This is going to basically mimic what should happen if you flipped a coin in a fair way every single time. So I'm not going to be very exciting. I'm going to flip a regular penny. If you'd like, you can select some other type of currency, but just make sure you're using the same thing as heads and tails every time. So this is going to flip 10 coins at once, so that's pretty handy. So what this would look like on my own paper is, let's see, 1, 2, 3, 4, 5, 6 heads. That means 4 tails, 40% tails. So not exactly 50%, but not too insanely off either. So then you'll flip this again, and so then we have 6 heads again and 4 tails again. So here are the results of what was found in class last semester. Every student, they actually had to flip a coin since they were in class, but they flipped a coin 10 times and then they recorded the percentage of tails that they had gotten. So this group, pretty unusual, 9 tails, not impossible though, unusual is pretty tricky in the long run. So just eyeballing these down, we've got some that are overshooting, some that are undershooting, and then some that are exactly 50%. Well, if you pull all these together, you end up getting 147 tails out of 250. So that in general is a 58.8% tails. This is pretty close to 50%. 250 is not a lot of flips. In my opinion, something like around 100,000 or 1,000,000 would start to become what you consider a large number. But we don't encounter these in general. We just know over time, eventually, we flip a coin, you could get a heads, we could get a tails. They're both pretty likely. So using this random coin flipper, I think it's going to be pretty easy to complete this portion of the assignment quickly. It's out of 10, so the percentages will be nice, and then you just need to make sure that you figure out your overall percentage for your tails. So let's go back. All right, so let's practice a few of these concepts. Everything that we're doing here is more technical than it is, kind of mathematics. But it's really important that you do understand this notation. You will see it when you Google search it. You'll see it when you are looking at probabilities in an article. But the article usually won't get technical because most people don't have the knowledge that you'll have when you leave this class about probabilities, especially with statistics, so of course. So there's an 80% chance of rain today. The way that we would interpret this is that approximately every 80 out of 100 days with these conditions will have rain. So people usually, give the weather people a lot of flack, but it's really difficult to predict the weather because there's so many variables, there's so many things that change over time. Honestly, with what I know about weather, which really isn't too much, I'm pretty impressed that they can predict it the accuracy that they do. And usually when I say that, students are kind of looking at me like I'm crazy, but it is pretty impressive that they are able to predict, I don't know, with so many things that are happening at the same time. So this is the same thing as 4 out of every 5. So if you like 0.8, I would still convert that to a percentage personally, but 80 over 100 and reduce that as much as you'd like. So this one is a statistic from the American Sexual Health Association. It's a statistics because it's not a census, right? We don't know every teen ever currently and how many of them have gotten an STD. That would be kind of weird. We'd have to have some sort of tracking device on people. So one thing that's important to note here is that 25 out of 100, so 1 out of 4 randomly selected teens will contract an STD in a given year. Random is really important here because if you have people that have similar characteristics, right? So you're looking at a group of friends that, maybe they're kind of on the more conservative side. They're less likely to engage in similar behaviors. They're less likely to be promiscuous if they're the similar types of people. So it has to be randomly selected. A good example I have of this is that I was at a Walmart picking out a carton of eggs, and I picked out the first carton and there was a broken egg, and I set it to the side. And I picked up a second carton and I set it to the side because there was a broken egg in that one too. And I actually went to 4 cartons in a row. And so my husband said to me, "Hey, what are the chances of that?" Just, making a statistics joke whenever he could. But I said, well, actually, the probability is pretty good that they're all broken because they were probably in the same crate. They had the same, traveling characteristics. So they're not completely independent at all. So that's probably a pretty, I would probably look at the probability in that case of 1 carton of eggs being damaged if the other one in that case is damaged, or the probability that a carton of eggs is damaged in an entire truckload. So those are the kinds of things you need to think of. Random is going to become super important because if things affect each other, their probabilities are going to be changed severely. So you flip a coin 3 times, list the sample space for this event, and then state the total number of outcomes. So I'm going to go over a few things on this slide, and the first is a tree diagram. A tree diagram is just a method of organization and showing your work. This is not the sample space at all, but it's really handy because some of the events that you can look at can have a lot of things going on, and it's not always really straightforward to figure out what each of your options are. So you flip a coin 3 times. You can get heads or tails the first time, you can get heads or tails the second time, and you can get heads or tails the third time. But if you wanted to describe every single part of that event, that can get kind of confusing. So I actually do a combination of this. I don't make a tree very often. It's usually when the event is kind of unique. But if you think about it as what I call fixing, so I say, okay, first I'm going to get 3 heads. There's only one way I can do that, heads, heads, heads. Then I'm going to look at all the ways I can get 2 heads. So I can get the tails last, 2 heads first. I can get the tails second, and I can get heads first and third. Or I can get the tails first and then get heads the last 2. And then I keep going and say, okay, well, how many ways can I get only 1 head? So I can get the head first and then 2 tails. I can get the head second and then 2 tails. Or I can get the head last and the first 2 could be tails. And then we're left with how many ways can you get no heads, which is just 1. Well, what the tree diagram does is it's a way to set this up so that it's visual and also very organized. So my fixing method is good if you're really confident in the process that you're doing. So I'm flipping a coin 3 times. That's a pretty common event. So if you wanted to take your tree diagram, you would get heads, 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 and this is why the one on the right is out of order than what I said. So heads, 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 follow the branches for that first path. And then heads, heads, tails is that second outcome here. Heads, tails, heads, heads, tails, tails. And then you repeat that. Everything is the same with just with tails first is honestly the big difference. So tails, heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. So the solution here, this is the sample space, and there are 8 outcomes. It's really important to understand how many outcomes are in your event. It's usually just as important if you need to know exactly all of them, what all of those outcomes are specifically. So flip a coin and then roll a die, a pretty similar event. The sample space for this, if you made a tree diagram, would be the first part of the tree would be heads or tails, and then with each of those outcomes, when you roll the die after that, you could get a 1 through 6. So if you roll the head first, you can get a 1 through 6. If you roll the tails first, then you could get a 1 through 6. I think that this is a better fixing method example. So first I fix the first roll to heads, and then I say, okay, heads, and then I can get a 1, 2, 3, 4, 5, or 6 with my die roll. Or I could fix my first roll to tails and then get 1, 2, 3, 4, 5, 6. So remember, we're not saying this has actually happened. We're just looking at all possible things that can happen when you roll a die and flip a coin together. So state the probability of the given events. The temperature of a randomly selected day last year was 315 degrees Fahrenheit. Well, If this was the temperature outside, we would cook. So this is going to be an impossible event, and not because we could cook outside in it, but because if it did happen, or we're looking at what happened last year, and we know that that didn't happen. So that would be pretty popular in the news there. Say the probability of the given event, the probability that there were 7 days in the week last week. So as far as we know, I mean, I guess technically if you wanted to get to like the beginning of time, maybe there are some cases where the man-made scale, if we still have to apply the man-made scale even though it wouldn't have existed yet. Technically, maybe the orbit of the Earth was a little bit different. So, but in general, it's certain to occur because of all the time that we've been collecting records, there's definitely been 7 days in the last week. According to the NHTSA, which is the National Highway Transportation and Safety Administration, of the vehicular fatalities in 2010, 16,824 were drivers, 6,404 were passengers, and 4,502 were motorcyclists. 65 were unknown. So the unknown can be something like bad paperwork. I mean, I guess technically if two people were thrown from the car, it's possible that they didn't know who was the driver in that case. But you know, it's more likely that it was bad paperwork, in my opinion. So find the probability that a randomly selected fatality was a motorcyclist. Is this probability considered unusual? So one thing I recommend to think about is part over whole. So in this case, the parts is how many qualify, which in this case would be 4,502 motorcyclists. And then the total is if you add up every single person that is possible here. So it was 4,502 out of a total of 27,805. So this is a 0.619 probability. That is 61.9%. I apologize, I'll have to put a note in there about that. And then this is not unusual. The probability of occurring is not less than 0.05. So that's our cutoff, right? So this is 61.9%. You know what, let's just change that while we can. Why not? And so that is much higher than 5%, so that's not unusual. Find the probability that a randomly selected fatality was unknown. So this is something I'd want to calculate if I wanted to see if this is a problem, bad paperwork. Let's say we're attributing this to bad paperwork. Is this probability considered unusual? I hope it is, because if there's bad paperwork that often, that would be a bad sign. So there were 65 unknowns out of a total of 27,805. And that is 0.0023. And when you convert this to a percent, and nobody likes percents that are less than 1, but they exist a lot, especially in statistics. When you move this decimal over, you move it over 2 times. So basically what you're doing is you're multiplying this by 100% to convert it to a percentage. This is an unusual probability, which is good, because if my record keeping was really bad, I'd have to look into it and maybe do some kind of audit on it. So the probability is less than 0.05, so that does make it an unusual probability. So lastly, using example 2, find the probability that the outcome is 3 heads. Is it unusual to flip a coin and get 3 heads in a row? So this goes back to our first tree diagram here. And so what we find is that there are 8 possible outcomes, and there's only one way out of this that we get 3 heads. So 1 out of our 8 outcomes end up getting a total of 3 heads. It's the only way that we can do that. So the number of ways to get 3 heads, there's only one. There's 8 possible combinations in all. And then that's 12.5%. So now notice sometimes I'm converting to a percentage and sometimes I'm not. In my head, I guarantee you I always am. But a probability is this number right here. So I don't always convert to a percentage because that is just kind of glamour. It's not necessarily needed. But the probability is greater than 0.05, so that is not unusual to happen. So if you flip a coin, you get 3 heads in a row. Shouldn't be anything too wild. So that is the end of this lecture. Definitely make sure that you review this, even though it seems kind of trivial as you go through it in general, because the notation and other things like that are something that you can get stuck up on that is something that can be prevented. So in the future and future topics in this unit, we're going to get a little bit more fractiony. We're going to use our calculator. We're not going to do any conversions or anything like that. So definitely make sure that you practice these through on your own without the solutions present. And as always, feel free to email me if you have any questions.